Greetings from the U.S. National Academy of Engineering. My name is Guru Madhavan. I'm the Senior Director of NAE Programs and the Norm Augustine Senior Scholar in Systems Engineering. I welcome you to this session on engineering complex systems for climate change and energy transition with my colleague and co-chair, John Borite, who's the Executive Director of International Affairs at the U.S. National Academy of Sciences. We know that the concept and recognition of complex systems in research and practice is nearly a century old. However, the state of knowledge and practice in the design and management of complex systems is still evolving. The key intellectual and implementation challenge that remains is the need for unifiability. Unifiability means reflecting on interdependencies and adjacencies. It'll be necessary to devote considerable attention to how we can better engage with complex systems. This, in turn, relates to how we plan for inevitable surprises. Let me give you an example. A decade ago, Japan's peculiar electric grid stalled its recovery from the triple shock of an earthquake, a tsunami, and a nuclear accident at Fukushima. The afflicted northeastern parts of the country operated on German generators at 50 hertz. The unaffected southwestern regions, however, powered by the American units, ran at 60 hertz. This profound incompatibility gave rise to a profusion of disruptions felt worldwide. Power transfer became impossible when needed, exacerbating the after effects of the triple shock. Global automotive supply chains ground to a halt in many countries because of Japan's sudden inability to manufacture and export prime engineering ingredients for motor vehicles. And they included airbags, fuel injectors, specialty paint pigments, key molders, microchips. As software, sensors, and electronics gain more functionality, a concentrated failure in one region can swiftly spread into a distributed calamity. Such point-to-pervasive incidents have become recurrent and ruinous. E. coli can now spread from a back porch lunch gathering to contaminate a country. This happened in Scotland. And bats can topple Wall Street from the wilderness. Our vision often links to what we have experienced in the past. Consequently, when facing complex problems, we tend to revert to those tactics that we used to fight a previous emergency rather than comprehending a current one. For instance, the approaches deployed in the response to the Chernobyl nuclear disaster was too often used to try to mitigate the effects of the Fukushima disaster, even though the circumstances were materially different. Similarly, COVID-19, as we all know, had its fair share of comparisons to the influenza pandemic a century earlier. Such nexus scenarios create a confluence of disparate time horizons, competencies, cultures, and perspectives. As the physical and chemical processes of phase transition illustrate, something with one set of properties can transform into a very different state with disparate set of impacts. Such information complexity directly impact our ability to decipher the so-called state of the system. Let's look into private sector manufacturing, specifically aviation. Boeing completely had to rethink the production of the 787 Dreamliner after facing numerous delays due to fragmented supply chains. For example, Boeing didn't know who their suppliers were beyond the first tier, and thus could not directly diagnose and manage delays. Airbus, too, faced similar assembly issues. Cables were too short because there were no integrated design processes across suppliers, or the suppliers didn't use compatible computer-aided design packages. Such issues of fragmentation loom large when we have a wicked system as climate. But to me, they seem to link back to the notion of unifiability, which this panel will begin to consider. What implications do these dynamics have for how we equitably engineer, enhance, and engage with the systems that surround us? This thinking does tie closely to some of the work we are doing at the National Academy of Engineering, at the junction of people, systems, and culture. That is, not just focus on engineering for people, systems, and culture, but critically emphasizing the people, systems, and culture of engineering to make the profession itself more welcoming to a broader set of perspectives, philosophies, and participants. It's absolutely clear that we should be taking a much stronger approach in reinforcing that likening engineering only to technology and not sociology is like saying that evolution is only gene-based and not related to culture. And economics is about rationality and has nothing to do with behavior. If engineering's past was grounded in the Industrial Revolution, engineering's future must be about inclusive evolution. But our panelists know very well that technology and sociology are inseparable, especially on a subject like climate change and the trade-offs for trajectory of energy transition. First, Dr. Mary Jane Bopape will start us off with her experiences with the South African Environmental Observation Network and comment on the vital need for a research infrastructure, especially in the developing world. Next, Dr. Robin Grimes from the Imperial College and the British Royal Society will present some pathways for decarbonization using nuclear energy. Following him is Dr. Chandrakant Patel from HV Labs, who notes how a return to the fundamentals of energy engineering will be a far more crucial requisite than getting trapped with the trends. Subsequently, Dr. Abubakar Sambao will take us through some considerations building on his experience as a former energy commissioner for Nigeria in developing appropriate technology use cases and uses. And finally, Dr. Azad Madni, who will, from the University of Southern California, discuss how do we build the essential competencies and capabilities and what's an offer with a transdisciplinary systems engineering perspective. Their viewpoints certainly will offer opportunities for synthesis and reflections, and Dr. John Borite will make an initial attempt at that. He'll then moderate the ensuing live discussions. We thank you all for joining us from different time zones and amidst different commitments. Now, let's get started.
Good morning, good afternoon, and good evening, colleagues, depending on where you are. I want to start by thanking the organizers of the session, Dr. Madhavan, as well as Dr. Borite, for inviting me to contribute to this important discussion. My contributions today will be to share with you challenges we have due to a space observation network on the African continent, and I will conclude my contributions by showing you initiatives we have in South Africa to deal with this challenge. I thought I would start by showing results from the latest Intergovernmental Panel on Climate Change. The report was published last year, and it indicates that climate change is indeed happening. We have been observing an increase in the mean air temperature as well as an increase in the number of extreme heat events, and these are expected to continue going forward. When we look at precipitation itself, there is generally no robust signal. However, where there is a signal, we are expecting to see a decrease in mean precipitation. When looking at the heavy precipitation events as well as pluvial flooding, there is a projection for an increase in such events, and this in itself suggests that we are going to see more damage due to extreme weather events. The report on impacts has also been published, and what you are seeing there are impacts across the globe, and where you see a negative, that shows that we are going to see adverse impacts, and where you see positive, that shows we are going to see a positive impact due to climate change. Focusing specifically on impacts on cities, settlements, and infrastructure, and looking at Africa, what we are seeing are negatives everywhere, which shows that we are going to see negative impacts inland, in coastal areas, negative impacts to infrastructure, as well as damage to key economic sectors. The information that we have in forecasting in general or projections is informed by numerical models. these numerical models have to represent the complex Earth system. They have to represent what is happening in the oceans, what is happening over land. So that is, looking at vegetation, looking at the hydrology, looking at how us as human beings interact with our environment. And for us to be able to run these models with high resolution, we need supercomputers. And these models are informed by what we understand from the observation networks. So we need an observation network to first understand the processes. And once we understand the processes, we represent them in models. And we need observations to initialize the models as well as to verify these models. This slide shows us what the state of the observations is across the globe. The first one on the left shows you the observations that were sent on a particular day. For this example, is 21 September 2020 that were sent to the European Centre to inform numerical weather prediction models. And the one on the right shows you the long-term observations that are sub-daily that are made available by the UK Met Office Hadley Centre. And what is coming out is that there are limited observations in the Southern Hemisphere. And when you look at the African continent, you can see that there is a very limited observation network. Satellite information is used to supplement ground observations, and in this slide I want to show you what we are finding when we want to do our model verifications. I'll start with the first column there that focuses on Botswana. What you see in the top left corner are ground observations from the Botswana Meteorological Services, and followed by that we have got a rainfall product from NASA, and below that we have a rainfall product from the University of Reading, and left of it we have a rainfall product from the ECMWF, which are the reanalysis that combine observations as well as the models. What these different plots are supposed to show are rainfall over a 24-hour period on a particular day. So this is supposed to be the same day, and you can see from this that the different satellite products as well as the reanalysis show different things, and this is because there are no ground observations to calibrate this information. This is a result that we found not just for Botswana, but we found it also for Zambia as well as for Namibia. For the Namibia example, which is is what on the right hand side, again the top we have got the observations, the ECMWF one, the NASA product, as well as the University of Reading product, again showing different amounts of rainfall in different areas being associated with high levels of rainfall. And these are observations that we need to use to compare against a different model simulations. So what you see below there are different simulations that I made that I wanted to compare against the observations, and you can see we've got a really big challenge if the observations themselves are very different from one another. I'll then start talking to the initiatives we have in South Africa, focusing specifically on the South African Environmental Observation Network, SION. SION is a business unit of the National Research Foundation. SION was established in 2002 with a vision to provide and establish world-class environmental research platforms for a sustainable society. SION conducts transdisciplinary research in ecology, socioecology, hydrology, meteorology, and oceanography. At the moment, SION has 7 nodes that are distributed across the country. We have 4 nodes that are focusing on the terrestrial side of things, and we have got 2 nodes that are focusing on marine sciences, and we have a node that focuses on information, communication, and technology in general, and we also have a national office. These nodes have been established and they've been placed strategically so that we are able to study different vegetation types over South Africa, so that we can also study the impacts of vegetation as well as study natural as well as human-induced impacts on the environment. The South African government, through the Department of Science and Innovation, has started running a program that they call the South African Research Infrastructure Roadmap. This program is aimed as providing South African researchers with competitive equipment and facilities that are too large or long-term to be managed effectively by an individual institution. 13 research infrastructures have been identified, and 5 of these are within the environment sector, and 3 of them are hosted by SION, and I'll speak to these 3 shortly. I will start with the Expanded Freshwater and Terrestrial Environmental Observation Network, which is one of the 3 that focuses on the terrestrial side. 6 landscapes have been identified following a rigorous proposal writing as well as review process. And from these 6 landscapes, there will be a number of platforms that will ensure that we take multidisciplinary observations. So these will include biogeochemistry, hydrology, meteorology, and atmospheric sciences, biodiversity, as well as social ecological systems. The second one is the Shallow Marine and Coastal Research Infrastructure, SMECRI, which is the most mature of the 3. Through this SMECRI, we want to be able to take measurements across the whole of the coastline of South Africa. We have got a number of platforms that ensure that we take essential ocean variables as well as essential biodiversity variables. We have got a number of platforms that include an aircraft. We've got a biochemistry lab. We've got a hyperbaric chamber that helps with diving, and we also have a data management platform. We also have the South African Polar Research Infrastructure, and through this RI, we are going to ensure that we've got long-term observations in the ocean. So this includes sea ice observations in the deep oceans, in the 3 oceans that are surrounding South Africa. We are also going to be ensuring that the long-term observations over land in Sinai, in Marion Island, as well as in Antarctica are there. Those that are there, they then are maintained properly. We will also be establishing a polar lab in collaboration with the University of Cape. Now, when you combine what SION is doing as well as the 3 research infrastructures, we are therefore able to cover different areas over the terrestrial side as well as over the marine side, going all the way from South Africa to Antarctica. It is important to us that our data is available following open science principles. So we have got a portal, and we have got a repository in which we also make available data sets that we do not collect ourselves at SION. So our data is available on our open science platform, and it can be downloaded for use by scientists locally in South Africa and across the globe. Thank you very much.
Hello, my name is Robin Grimes. I'm from Imperial College, but also representing the Royal Society. Today I'm going to be talking to you about pathways for decarbonisation using nuclear energy. I'm starting with 2 diagrams, one of which is showing the carbon intensity across different countries in Europe. And on the right-hand side, the energy generation mix that's giving rise to that difference in carbon intensities. Now, there are some regions which are very green, indicating low carbon intensity, and those are countries that have really good access to either hydro or nuclear. But of course, there aren't mountains in every country, so not all countries have access to really good hydro in particular. There's also an issue with the intermittency of wind, which limits carbon benefits because during times when there's no wind, then the difference in requirements is made up by burning fossil fuels. There's another point, and I'm using the UK as an example here. And on the left-hand side, you'll see that the amount of electricity generated as a percentage of the total energy used in the UK is only 17%. That often comes as a surprise to people. Actually, most of the energy, 40%, is in transport and 43% is in heating, different sorts of heating, domestic heating, and also for industry. On the right-hand side, I'm really emphasizing again this issue about the intermittency. Now, this is a particular day, and the days vary tremendously. But while we have nuclear in the UK, we have quite a lot of wind in the UK. The nuclear is always there, but the wind varies. And as a consequence, and because the demand for electricity changes as well, there is a big fluctuation in the amount of gas that is burnt to make up the difference for our requirements. Okay. See how we expect things to go, because remember, we're all driving our way towards a reduction, perhaps to net zero in terms of carbon production. So future energy markets are going to be really dominated by this drive. Initially, we're in this position of starting to see more electric vehicles, greater demand for electricity, e-fuels, hydrogen production by electrolysis, again, an increase in electricity demands. So lots more clean electricity. As we drive towards net zero, we're going to see much deeper solutions for decarbonising that heat and transport. And eventually, we want to see the entire network, probably towards 2050. So the real question for nuclear is, in a grid that is dominated by intermittent renewables, how does nuclear contribute? And that's what I want to go on to now. Now, at the Royal Society, we've been thinking about this for a while, and I just want to give you the reference for a report that we wrote, Nuclear Cogeneration, Civil Nuclear Energy in a Low Carbon Future. And a lot of what I'm going to talk about now comes from that report. So new nuclear must be able to help this issue of intermittent renewables. And the key thing you need to remember is that 65% of the energy generated by nuclear, and in fact, in any way, when you warm water to produce steam and drive a turbine, that is waste heat. Now, the waste heat can be used in a number of different ways. We could do district heating, for example. If we had higher temperatures, we could do some forms of process heating. We could also use the electricity directly to produce hydrogen. So there are numbers of options that we have, but we also have a number of different reactor types, and I'm going to be talking about that with regard to different reactors doing different jobs. But first of all, I want to introduce you to this concept of the temperature you require for the heat to do different industrial processes. Right at the top, we have glass making, which demands the highest temperatures because, of course, you've got to melt the glass. We then have petroleum refining, methane reforming, steam hydrolysis, electrolysis, which is going to be very important because that's going to be part of the way that we produce hydrogen in the future. But right down at the lower temperatures, we've got things like desalination and district heating. So different reactor types are going to contribute to the heat that you need for those different industrial processes at different temperatures. Now, the different reactor types, and you saw them there at the bottom of that last figure, are things like small modular reactors, but also then advanced modular reactors. So what are these? Well, small modular reactors are quite conventional, so they have conventional nuclear technology heat output. And that's relatively lower temperature, similar to any form of generation where you're producing steam. And so they are limited in what they can do, but they are still important as part of the solution. Advanced modular reactors, we aim to go to much higher temperatures, those high temperatures required for those demanding industrial processes. So that's part of the solution. In addition to that, we want to look at things like synthetic fuel production. And so I wanted to spend just a couple of minutes explaining about that. So just here, we need a source of hydrogen. So we can use the electricity from our reactor to use by electrolysis to produce our hydrogen. We then got to form, we generate the carbon dioxide in some way, perhaps by direct air capture from the atmosphere. You can then use those via a chemistry route to form your sustainable fuel. So straight away on this diagram, you're seeing that the nuclear reactor is being used directly to produce hydrogen, which we can then burn or use as a transport fuel. But we're also using that reactor in the output to look at ways to produce sustainable zero net carbon fuels. But there's another issue here that's very important. The point is that we want to use the reactors producing electricity when we need that electricity, because the grid demands that electricity. But when requirements fall back at different times of the day or different times of the year, we can then use the output from the nuclear reactors to generate hydrogen, to generate sustainable fuels. And that's the co-generation part of the solution. What are we going to be looking out for in the future? Well, first of all, nuclear power stations that are designed not just to produce electricity, but produce other things. We are going to look for nuclear reactors that are probably smaller in size. Nuclear reactors that are designed for all aspects of the life cycle. For build, because we want to be able to build them more efficiently, but also at the end of the life cycle, we want to be able to dismantle the reactors in a safe way that allows us either to reuse materials from those reactors or safely deal with the waste. We're probably going to see new nuclear reactors, different new places, which will require us to think about the civil engineering. Seismic rafts is an example of that. We want to shorten the construction periods for these reactors. We want to be able to use factories to produce a lot of the components, and this will lead, we hope, to shorter construction time. Now, it's always very dangerous to create something like a roadmap, but nevertheless, I'm going to try to offer some thoughts on this. The first thing is I wanted to emphasize is we haven't given up on the very large gigawatt reactor production, because remember, we need that constant base load of electricity that is required all the time, 24/7. We're then going to look at these smaller reactors, which are going to be more flexible, these small modular reactors, but they have some limitations because the heat output, like the gigawatt reactors, is at the lower end of our requirements. More activities to understand how to build and understand how to operate advanced modular reactors will give us access to higher temperatures, which means we can use the heat directly and thus more efficiently for industrial processes. And then eventually, and this is a very difficult thing to do, those high temperatures will also be produced by fusion reactors. So that's the end of my presentation today. Nuclear cogeneration. Key points are increased requirements for zero carbon baseload electricity, the question of how does nuclear contribute, and it must contribute, if it's going to contribute, by dealing with the intermittency challenge of renewables. We can do that by using the heat directly or using the heat to generate electricity. So to balance the intermittency in that manner, we need small modular reactors initially with greater flexibility, and then later advanced modular reactors with higher temperatures, perhaps eventually leading to fusion energy. Well, thank you very much for listening to me.
Greetings, everyone. In my talk today, I present a fundamentals-based holistic framework that uses joules of available energy as currency. When I think of available energy in our conversations at home, I always go back to the source, the supply side. So in this picture, when we think of the joules per second coming out of the outlet, we really go back all the way to the joules that are available at the height of the dam. So the potential energy of water is the available energy from second law. And that availability is destroyed. That available energy or exergy is destroyed as the water rushes down the penstock and there are irreversibilities. And then various conversion and distribution losses. And ultimately, the joules per second come out of my outlet, go into my laptop, multiple conversions later, only 10 to 15% of available energy at the height of the dam has made it into the chip. So it's available energy at the source. And if the source happens to be natural gas, it is 45 megajoules per kilogram. A framework for sustainability. So here I introduced a fundamentals-based holistic sustainability framework. The framework consists of three salient points: supply side, demand side, and integrated supply-demand management. The principles of the supply sides are threefold. On the supply side, first, consider the available energy, as we described earlier. The potential energy at the height of the dam, as it's shown here in this sketch, or 45 megajoules per kilogram in diesel, natural gas, that's available. And use that available energy as first principle to account for available energy used across the lifetime of a product. So cradle to cradle available energy used to extract materials that made this device, the manufacturing, the available energy needed to manufacture the device. We are also big on negative externality. So in making the device, there was pollution that might be created. The pollution that is created must be mitigated, because that becomes a burden to society, a negative externality in economic terms. So available energy required to mitigate the waste must be added to the cost of the product, which is being calculated in joules. So joules of available energy in extraction, joules of available energy in manufacturing, joules of available energy required to mitigate the waste and return the environment back to its state, joules of available energy in operation and in reclamation. You might say the biggest negative externality we face is climate. We decided to create a supply chain that gave us low-cost goods, but we created a negative externality which has become a huge burden to society. That's why negative externalities are critical. So that's the first principle. Second principle, use local sources of available energy. So if I'm building something, whether it's a factory or even my house, I should look at what is available locally and may have a microgrid in that context. So available energy from sun and other sources could be available energy from biogas, waste stream. I might locate my factory near a source of waste, and then I can use available energy in waste stream. In using available energy in waste stream, I must use second law analysis to determine what is available. So those are the first three principles of supply side. Cradle to cradle accounting of available energy, all the way back to cradle, local sources of available energy in waste stream. On the demand side, provision the resources on the demand side based on the needs of the user and shape the demand based on the supply available. So the simplest explanation is, if I gave you a barrel of joules, the barrel of available energy in joules, let's say joules of available energy at 1 kilowatt per square meter impinging on a solar panel, converting, or other sources of available energy, and you had a barrel of available energy, How will you shape your demand so that you are net zero? That's what integrated supply demand is all about. Shape your demand based on the needs of the user and keeping in mind what is available on the supply side. So those are the principles. Now I'm going to go ahead and elucidate these principles via some examples. But before I do that, I introduced the topic of introduced waste stream as a key element of our principle. And when we think of waste stream, it is important to go back to fundamentals and use second law. For example, hot gases coming out of a chimney have tremendous available energy if they are at a high temperature. So 1 joule at 500 degrees Celsius waste stream still has 0.6 joules that's available. We ought to utilize it as high grade available energy. We need to return back to the way we were in this type of analysis, as we always did in the past. Now, by the same token, 1 joule at 50 degrees Celsius only has 0.077 joules available. Low grade. So exhaust air coming out of a laptop or a server is low grade. We have to match that low grade with something on the demand side that is appropriate. So, or use it in some other location appropriately. So it's very critical to examine and utilize available energy in waste stream. So now that we have defined the framework, let's go look at some of the examples. First example is cradle to cradle joules of available energy. So in this case, consider something like a laptop. The joules of available energy required from cradle to gate. How will you design the laptop so that it is modular, long-lasting, and has been shaped? The cooling system and various other systems, including the power system, have been shaped properly to drive efficiency. How will you, from gate to grave, during operation, how will you minimize the consumption of available energy? How will you look at data from the laptop and do diagnostics and prognostics and self-healing? And then how will you take back the components from the laptop? So that's the way to think about the overall laptop. And to say that this laptop is not in dollar terms, but rather 9 gigajoules of available energy consumed from cradle to cradle. Now let's consider some examples of integrated supply demand management. In this first example, consider a net zero digital manufacturing factory populated with additive manufacturing machines, 3D printing machines. 100 of them take a megawatt of power. So that megawatt of power is provided by a supply side grid. And the supply side grid is made up of solar, and the 3D additive manufacturing factory is located at a dairy farm. 2,000 dairy cows produce sufficient manure, the anaerobic digestion of which to methane and then conversion to electricity will power the entire factory. So now we have a supply side grid with steady power from manure and diurnal power from sun. Shift over to the demand side. On the demand side, I allocate the workloads based on the service level agreement with the customer and shape the demand so that I'm below the supply side curve. An example of integrated supply demand management and net zero factory. Now let's shift our attention to California highways. Interstate 5, imagine that's an electric highway with all electric vehicles. The California aqueduct flanks that highway. The 600 kilometer long approximately can be covered with solar panels, a gigawatt potential. And in the same area, in this picture I took from the airplane, are dairy farms in the Central Valley. The manure from dairy cows converted to electricity, methane and electricity, becomes the supply side grid for the vehicles traversing the Interstate 5. That's the supply side. On the demand side, intelligent vehicle management with vehicle-to-vehicle communication and speed adjustment can lead to demand shaping that we can realize net zero highways in California running on integrated supply demand management. And then finally, I want to share with you an example from our daily lives at the Patel household. In the Patel household, we use net positive impact as a metric. It's a dimensionless metrics, joules over joules. So in this example, the clothespin used to dry clothes, we've been using them for 20 years. These clothespins have saved a great deal of joules in natural gas and electricity because we didn't use the dryer. That goes in the numerator. On the denominator goes the joules of available energy used cradle to cradle for the clothespin. The net positive impact is huge. So the humble clothespin stands out as an example of great net positive impact. I thank you for listening intently. I hope you enjoyed this conversation on integrated supply-demand management.
I'm very delighted to be at this very important IAP conference. And as I begin, I bring greetings from the Nigerian Academy of Science, where I am the Vice President. I also bring greetings from Usman Danfodio University, Sokoto, where I am a professor at the Faculty of Engineering and Environmental Design. Now, Nigeria's current population figure as obtained from United Nations Information Data Bank is about 270 million. But the electricity supply is at best 5,000 megawatts through the national grid. And this gives an annual average electricity consumption per capita of the nation of at best 200 kilowatt hour. This is extremely low when it is compared with the world average figure, which is about 4,000 kilowatt hour. Even the sub-Saharan African average figure is 500 kilowatt hour, which means Nigeria is just about 40% of the level of supply of sub-Saharan African countries, averagely. Now, this is really very inadequate for sustainable growth and development of the nation. If we look at the other major class of energy supplies, that is transportation fuels, we see the situation is also very bad. This is because Nigeria, despite being a major oil producing country, the 4 government refineries with a combined refining capacity of 445,000 barrels per day are all out of service. The one type of problem or the other. And all the petroleum products requirements of Nigeria today are being imported in the country at great cost. Now, the massive inadequacies in electricity supply and in the supply of oil and gas for the transport sector is the reason why many Nigerians today see the energy transition plan occasioned by climate change considerations as a very good opportunity for the country to solve its huge energy deficits. Indeed, Nigeria's energy transition plan is necessary because of the serious implications of climate change. In the northern part of the country, desertification is very clear, while in the central parts, and in fact some parts of the north and south, there is serious problem of flooding that comes with the devastating consequences of destroying homes and farmlands with several planted crops. In the south, the problem is more of soil erosion occasioned by socioeconomic consequences. And all of this point to the fact that bold actions to mitigate consequences of climate change must be undertaken with all seriousness. In light of rapidly rising population, accelerated development is needed to ensure improved living conditions for Nigerians. This means that the next 2 to 3 decades present unique opportunities to merge these two priorities, which are that of economic development on the one hand and that of climate change mitigation on the other hand, so that achievement of just energy transition can be realized in Nigeria, which is Africa's largest economy at the moment. At the Glasgow Climate Change Conference, COP26, in November last year, our President Muhammadu Buhari, announced Nigeria's commitment to carbon neutrality by 2060, and the nation's energy transition plan was subsequently unveiled, highlighting the scale of efforts required to achieve net zero by 2060, while also, as I said, meeting its energy needs. Since that announcement, Nigeria's Climate Change Act 2021 was passed into law by the nation's parliament, and the Energy Transition Plan was submitted to the Federal Executive Council of Ministers, which they, after due consultation, approved as well. The Energy Transition Working Group has been set up with the country's Vice President as chairman and several key ministers as members, as well as some senior officials of government and a few from the private sector also as members, supported by the Energy Transition Office. Now, Nigeria's Energy Transition Plan document can be really described as homegrown, data-packed, multi-pronged strategy developed for achievement of net zero emissions in terms of the nation's energy consumption. It sets out timelines and frameworks for attainment of emission reduction in 5 sectors. And the sectors are that of power, cooking, oil and gas, transport, and industry. And the major objectives of the plan are: number one, to lift about 100 million Nigerians out of poverty. Secondly, to bring modern energy services to Nigerians. And thirdly, to manage the expected long-term job losses in the oil sector due to the impending global reduction in the demand for oil. And number 4 will be to continue providing leadership role in Africa by advocating fair, inclusive, and just energy transition. Last but not the least is the objective of streamlining existing and new government energy transition initiatives. I'm very glad to say that the tremendous gas resources of Nigeria, confirmed to be about 206 trillion standard cubic feet, with the unconfirmed figure about 3 times that, has been accepted by all the other 17 oil and gas producing countries of Africa and the European Union as a transition fuel. It should be stressed that one of the outcomes of the energy transition plan, as mentioned earlier, is job creation potential, which estimates show that about 340,000 jobs will be created by year 2030, and the figure will rise to about 840,000 jobs by the year 2060. This is expected to manifest mainly from the power, cooking, and transport sectors. Gas as I've just mentioned, will play a critical role in the transition plan, especially in the power and cooking sectors. This is to come from the significant investment opportunities for the establishment and expansion of industries related to solar energy, hydrogen, and electric vehicles. It is useful to note that the emission reduction potential of the energy transition plan of Nigeria is such that the computed total emissions of the country of about 180 million tons of carbon dioxide equivalent will be reduced to 15 million tons of carbon dioxide equivalent by 2050, which was the initial net zero target. But given the significant financial, social, and technological requirements, the nation concluded that a more realistic pathway for enhanced decarbonization will be 2060. It has been estimated that Nigeria will require about 1.9 trillion US dollars to attain net zero by 2060. And this figure has been shown to be about 410 billion US dollars, billion dollars above normal expenditure, which works out to be about 10 billion US dollars per annum from year 2021 when the initiative started to year 2060, our net zero target date. When the energy transition plan was launched 2 months ago, that's in August this year, both the United States of America and the United Nations describe it as to be launched in Africa and presented to the general public of the country. Progress in the implementation of the Nigerian Energy Transition Plan is expected to be formally presented at next month's Climate Change Conference, that is COP27 in Egypt, Sharm el-Sheikh, Egypt. And I hope as many of us as possible will be there to participate in the major yearly global event, which was only posted during the peak of the COVID-19 pandemic. I thank you all for your attention.
Hello, everyone. I'm delighted to attend this IAP Triennial Conference on Engineering Complex Systems for Climate Change and Energy Transition. My talk today will be on transdisciplinary systems engineering education for studying climate change and energy transition. Before I get going, I'd like to share a few particulars about me. I'm a university professor and the executive director of the Systems Architecting and Engineering program at the University of Southern California, as well as an NAE member. I study systems engineering as part of my doctoral degree major in engineering systems at UCLA. My research and education perspectives in systems engineering were influenced by the works of Norbert Wiener in cybernetics, Claude Shannon in information theory, Ludwig von Bertalanffy in general systems theory. I've conducted research in intelligent systems engineering for 40 plus years, and I'm an active researcher and educator in the field. My research has been sponsored by both government and aerospace and automotive industries. I have written and edited several books on systems engineering, including Transdisciplinary Systems Engineering, published by Springer in 2018. Transdisciplinary Systems Engineering is a key enabler in the study of complex socio-technical problems such as climate change and energy transition. I'd like to share a systems perspective on the problem of climate change and energy transition. First and foremost, these problems are global socio-technical systems problems with known and unknown interdependencies and interactions. They require an understanding of how humans and societies are likely to react to interventions, because these interventions can produce unexpected behaviors. They cut across multiple disciplines and have multiple dimensions. The impacts of interventions that we make in these complex systems are only partially known, because there can be ripple effects that can produce unintended consequences. This kind of a problem is generally described as a wicked problem. A wicked problem requires the management of complexity and uncertainty at the intersection of science, technology, economics, politics, ethics, and yes, human behavior. In a wicked problem, the problem morphs continuously with interventions made. Therefore, with that particular characteristic, the problem can only be managed, not solved in the traditional sense. If you look at pandemic management that we've just gone through recently for the last 2.5, 3 years, it's a classic example of a wicked problem. The problem of climate change and energy transition is a much larger scale problem than pandemic management. It ultimately requires interdisciplinary, holistic thinking that needs to be reflected in engineering curricula and learning strategies. Now that I have shared my ideas of climate change from a systems perspective, I'd like to talk about the implications of these characteristics. First and foremost, there are multiple measures to study climate change: agriculture and environment, atmospheric science, environmental horticulture and urban forestry, ecological management and restoration, environmental policy analysis and planning, environmental science and management, environmental toxicology, hydrology, sustainable agriculture and food systems, sustainable environmental design, and many more. We can't possibly study all these majors. Therefore, we need to think about it in a different way. And that is to think beyond and across disciplinary boundaries. To do that requires a new mindset, rooted in understanding where the synergies exist among disciplines and how they can be exploited in addressing climate change and energy transition problems. It begins with understanding problem contexts and how disciplines can interface with each other in different contexts. It means revising engineering curricula to replace existing stovepipe courses with interdisciplinary courses and or incorporating content from synergistic disciplines into existing courses. It also means looking to exploit relevant concepts and apt analogies from other disciplines in problem framing and system architecting in engineering courses. On the earlier slide, I spoke about a new mindset. Now I'd like to describe the characteristics of this new mindset. First and foremost, we need to think holistically in terms of seeing the big picture and not in reductionist terms. We need to think in terms of self-organization and not organization design by some external agent, a person or software agent or something else. Given the complexity and constant changeability of the climate and the energy problem, we need to think in terms of agility and resilience and not just rely on traditional optimization methods. Once again, looking at the complexity of these problems, we need to think about scaling up the methods that we have today to be able to address these problems at scale and not dumb down the problem to fit some known technique that we know. We could, of course, do that, But if we did that, we would be solving a different problem, the wrong problem, and the real problem that we had would still be around. We need to think in terms of influencing and shaping the behavior of complex systems because they cannot be commanded and controlled like traditional simple systems. And that means being able to employ the proper incentives and inhibitors that result in influencing and shaping the behavior of humans and societies. We need to think in terms of mutual commitments and not just rely on contractual relationships that we have in the past. And importantly, we need to view humans as assets and not as liabilities to be shored up. When it comes to planning, we need to think in terms of plan adaptation, dynamic plan adaptation, and not end-to-end planning. Because as we all know, a plan does not survive the first contact with the enemy. We need to think in terms of exploiting the growing convergence among disciplines and not rely just on engineering. And what this amounts to is that this mindset underlies transdisciplinary systems engineering. To the right of these bullets, you see the book that I had written in 2018. Its subtitle is Exploiting Convergence in a Hyperconnected World. And now I'm going to go a little bit deeper and talk about how I have brought this method to life in engineering courses and engineering curricula. So what is transdisciplinary systems engineering? In my book, I define it as a meta-discipline that calls for a new mindset to exploit convergence of systems engineering with other disciplines to address problems that appear intractable when viewed solely through an engineering lens. Examples of these concepts from other disciplines are reinforcement learning from AI and machine learning, digital twin technology from digital engineering, the concept of preference, utility, and value from decision analysis, the concept of crowdsourcing from social networks, and the concepts of storytelling and animation from entertainment arts and cinematic arts. These concepts that I described earlier, I brought to life in an educational paradigm called TRACY. TRACY stands for Transdisciplinary Systems Engineering Education. It is specifically designed to break down stovepipe thinking and foster interdisciplinary thinking and leadership skills. The emphasis is on creating connected knowledge across courses. And that means that courses should have just enough content from synergistic disciplines to prevent the formation of islands of disconnected knowledge. Students are taught to exploit the synergy of engineering with other disciplines when addressing complex problems. Students are also taught methods from other disciplines that complement or enhance systems engineering. So here are my recommendations based on the foregoing discussion. Climate change and energy transition are socio-technical system problems with known and unknown interdependencies. These problems require the development of a theory of interventions, for example, the proper incentives and inhibitors, to influence the behavior of both individuals and societies. They require an understanding of how humans and societies are likely to react to interventions to reduce the likelihood of unexpected behaviors. Such problems require a combination of methods from different disciplines to appropriately frame problems and design interventions. They also require traditional reductionist approaches to be replaced with holistic transdisciplinary approaches. The current educational paradigm and the curricula needs to be extensively revised to reflect this new mindset. With the creation of TRACY educational paradigm that I have been using successfully in the University of Southern California Systems Architecting and Engineering program, I believe we are well on our way. So let me sum up what I've said so far with a few key imperatives. First, teach students to think holistically, which means see the big picture, understand multiple different types of relationships, and discern patterns. Second, look beyond engineering and siloed courses when creating course content to ensure that students acquire connected knowledge and not end up with disconnected islands of knowledge. The third is foster experiential learning. Employ educational infrastructure that enables combination of technological advances, learning sciences principles, and opportunities for hands-on learning within a storytelling rubric. Here are the references. For those of you interested, you can go back and refer to these and download them from Google Scholar or from your libraries. Here are additional references on each of the topics that I have discussed in my talk today, and these can also be found and downloaded from Google Scholar. And with that, I bring my talk to a close. Thank you for your kind attention, and I hope you have a wonderful rest of the conference.
Can I? I want to thank my colleagues who've just made these amazingly diverse presentations of this huge societal challenge. They are, several of them, in Europe and Africa right now, and are heroes to still be with us. I think 3 or 4 of them will be, so hopefully we can have some very useful question and answer. The design of the program called for me to make some synthetic remarks, and I'm sure you can see how difficult that is. Just a few very quick things. The presentation of Mary Jane Bopape about the process of understanding what's happening and what's likely to happen is, of course, critical for 2 reasons. One, we have to understand and convey to society and to governments what is happening and what is likely to happen. And that has to be very solid. And we all know the difficulties of making that in that case in democracies in particular. Secondly, we need that very detailed information to the degree possible to design our infrastructure. The infrastructure, take energy, which we're talking about in this session, like other infrastructure, it's an investment to cover decades. And so when you think about thinking ahead decades about the environment that this infrastructure is going to be performing in, that's a really major challenge and a very important one. Temperatures are going to be different. Extreme events are going to be different. There are going to be a whole set of issues at coastal areas, and these are going to compound each other. So the first point is that work done by the IPCC is extraordinarily important for this particular case. Robin Grimes has made, I think, a really very, very useful presentation addressing nuclear, but perhaps more basically and more importantly, the essential challenge as we increase solar and wind power. How do we make it all work out when those things are changing, and how do we do it in a way that doesn't waste power? And I personally kind of connect these presentations. The presentation on of Professor Patel on a approaching it in fundamentals, I guess I'd say in a little bit of a simple-minded way, it's largely about don't waste anything, including the heat at whatever level it's available, and so on. I do find it interesting that that Dr. Patel ends up with an example of human behavior making a significant change in the actual demand, and I think that's generalizable quite broadly to many choices that society, individuals, communities can make that will make some difference. I believe it's true, has been true for quite a long time, that investments on efficiency in electrical and other energy use have been one of the best investments, one of the highest investments on return on investments in the whole scene of energy. And I think, again, it's a question of being efficient, of minimizing losses, and of understanding the complexity of the situation. Professor Sambo, I really appreciate that presentation. We need a solid dose of reality as we face these issues. 100 million people in poverty is a serious reality that I find it gallant that the Nigerian government has put together a strategy that is aimed to achieve all that. And in terms of energy, there's much to talk about that, including the choice, which I think is made by many people, of gas as a transition. But of course, it's a long, complex process. Finally, I guess these are rather maybe over-ambitious comments, but it's interesting to have the last presentation on the education that we need to deal with this huge societal problem, and to think about, for example, to go back to Nigeria and Africa in general, an enormous youth bulge that in some ways, of course, is to be a benefit. You know, when you have a fraction of your society that is working, that is large compared to the fraction that is retired, that's in general a good thing. And so I'd be interested in questions or thoughts by the panelists about how can we successfully mobilize the kind of education that we heard from Dr. Madni in the last presentation. I think I'll stop there. We don't have very much time, and let's try to have some questions and answers.
Can they hear me on the push the mic? So thank you. I thought they were really interesting presentations. I had a question for Robin. This is Tom Solomon from the UK Academy of Medical Sciences. I just wondered how far down the journey we are in the UK with these different types of reactor, and also what the response of the government is to these different approaches, and also what the response of the people is, because there has been mixed attitudes in the past towards nuclear reactors. And my understanding is especially some of these small modular reactors would be there'd be lots of them in very local places, as it were, rather than previously where reactors have been in rather remote places.
Hi, Tom. And certainly, I'm very happy to talk to you about this offline, because it's a very long sort of question and a bit UK centric. So let me try and put it in sort of more broad terms for the broader audience. And what I tried to do is explain that the challenges of a stable grid in any country is actually a very complicated one, because you've got the demand fluctuations due to, for example, with solar, day, night, wind, how much it's blowing and things like that. But also, so the supply side, sorry. And then you've got the demand side, because there are times of the day when people need an awful lot more electricity. So trying to understand how things like small modular reactors, or reactors that are going to be swapping in and out of producing energy and then producing other products, has to be balanced in with those requirements. And also there's the issue of grid stability, which is another system within a system. And I was really struck by Guru's sort of comments at the beginning of this. And it's this complexity of how these different systems fit together. And in the UK, I think we are developing, but we've got an awful lot further to go to understand how you balance those different requirements and those different systems of systems against each other. And I think it's probably true for most countries. So I hope that was useful. But as I say, I'm happy to chat about that with you offline as well.
Thank you.
We have some very extensive comments and in the Q&A. The one of them is question to Robin. That was the acceptance of the public. Yeah, that is a question. Also, there was a reference to the nuclear fuel disposal issue. I would add to that a couple of things, if I could. One is the big picture is we're not really moving right now, almost at all, in what we need to do, in particular to get out of coal. And partly that's a very unfortunate accident of what's going on in history right now. But I find it hard to believe that we're going to make it without nuclear in a time scale that's relevant to avoiding really major climate catastrophe. But also back to Robin, there also is the question, there are many questions, I think, about all of these sources. Nuclear and some other sources, for example, they're going to have many decades of lifetime water supply. And when you think of projecting decades ahead for water supply, that's something of a serious question. Robin?
Yeah, no, absolutely. For example, there's been a set of reactors built in the UAE, and there they have the source of water is very salty, and it's also very hot. And so how do you cool the reactors in a very hot environment when your ultimate heat source is already a lot hotter than how the reactors were designed for in the first place? And I've been typing feverishly, and I didn't do a very long answer to the question on the nuclear waste, but somebody brought that up, which I thought was a really important question. When you look back at how reactors were originally built, nuclear waste issues were an afterthought that could be dealt with. And of course, that has caused all sorts of problems having gone forward, because, John, you're right, reactor systems, and nuclear is not alone in this, are systems which then operate for 50 or probably 60 years, the new designs. And of course, society has changed, and our requirements have changed, and the climate's changed. And then how you build that into the original thought processes, particularly given the complexity of the system's challenges, I think is very difficult indeed. I think others may probably have views about that.
with one eye on the clock. There's a comment, question for Dr. Madni. Well, I'll read it. The transdisciplinary system approach to tackle climate change and energy transition. Could he provide a sense of this approach on the impact of climate change on health policy implementations? I had meant to say that the excellent session earlier today on health and climate was actually highly relevant to this. And maybe I could add, is this approach for Dr. Madni something that only is going to need to be happening at the university level, or is it something that somehow is built into education earlier?
John, those are excellent questions, and I was just typing in my answer to Narendra, and so I'll just speak it out loud. No, I think this can be practiced outside of the university environment. It can be addressed by practitioners and industry. The key thing to remember here is when you talk about climate change, which interacts with so many different disciplines, and when you talk about health policy implementation, it's so important to reflect the constraints and the concepts of health policy implementation in the interventions that are designed, so that you don't end up having the opposite effect of what you intended. And so I think look upon it as a porous boundary between climate change and health policy, and see what policy concepts and constraints would have an effect in terms of realization of the policies you might suggest. And I think having this bi-directional mutual understanding between these two concepts would be a way forward. And I think it can be practiced not just in academia, but in industry. People such as Professor Patel, in the work that has been going on at HP and things like that. I think people have started to recognize that many problems require thinking that is holistic, and that was Jasek's question to me. And that means that maybe you don't structure these stroke-wide courses that you've had since time immemorial. Maybe it's time to redefine the courses more in terms of competencies taught, rather than techniques, taught in the courses. So people can think in terms of interdisciplinary within a course and not have to go back with disconnected islands of knowledge and try to connect them on their own after the fact.
Thank you. There is a question here for Mary Jane that has to do with whether insurance companies are accumulating data and knowledge, and do they make use of simulation results. And since we've not got much time, I would also ask whether you have, Mary Jane, any other point you'd like to make in any of this exchange, and also hopefully we'll go back to Professor Sambo if he wants to comment on any of this. So, Mary Jane.
I think that is one that is crucial, especially because, as I've already mentioned, we don't really have much in terms of observation. So I think where we've seen insurance helping is with, our lightning information. They do approach, for example, the South African Weather Service to seek such information. And we've also seen linkages. For example, if there's a storm that is approaching, the insurance companies would approach meteorological services and they use this information. They send messages, to their customers, so that, if, for example, if your car is parked outside and there's hailstorm that's coming, so that you can just move it out of harm's way. But I think in terms of observation collection themselves, we don't really see much that's coming from the insurance industry. They help us with hail information, because hail generally you can't observe it. So what we do with regarding hail is from the radar observation network, you are able to make estimation of how much hail is coming out. And for verification purposes, then you can get information from the insurance industry. The one point I just wanted to make is basically just to stress the need for observations, because when we say climate is changing, it's important that we know how much and how it is changing across the globe, and the information that we've got at the moment is really not complete. There are some areas that are not captured by the available observation. Thank you.
Thank you. Professor Sambo, would you like to comment on any of this? We've got a couple minutes, a few minutes left.
Yes.
And
yes. Thank you very much, John. First of all, I think I want to refer to what you mentioned. Our targets look very ambitious. I would say yes, because the energy poverty issue is so serious in Nigeria and much of Africa as well, especially sub-Saharan Africa. I'm sure you are aware electricity access of sub-Saharan Africa is only 43%, while that of the whole world is about 87%. And in the Nigerian Energy Transition Plan, two major considerations, as I've explained in my opening statement, were made. Number one, to solve the energy poverty, and number two, to attend to the climate issue. The energy poverty aspect is in line with addressing SDG 7 considerations. And as you know, every year, nations gather at the United Nations General Assembly. There's the discussion, the powerful side event of meeting the Sustainable Energy for All office. That's where the Energy Compact template is discussed. And on the other hand, the climate change issues are in line with the nationally determined contributions of our country. And all these are not done just by the government department. The private sector is there, the civil society organizations are there, and development partners together. In fact, the Energy Transition Council for the COP26 in Britain helped us significantly to come up with what I showcased. So it's not just ambitious, but reality. Mind you, the population is so huge, 217 million people at the moment. And that is why we are giving it all the serious attention it deserves. I quickly want to refer to Robin's presentation and to say I know in my zone of West Africa, Nigeria, Niger, and Ghana have nuclear power programs. And apart from trying to use nuclear to cater for our base load, we also note that it does not emit any carbon dioxide emissions. And once you load your fuel rods, you start your reactor, it goes for years. So this is what we are looking for. And on this note, I would like to get in touch with Robin Grimes in the nearest future so we can open line of discussion in that direction.
Thank you very much. We are at the time, and we do want to have the couple minutes for people to put in their feedback on the presentation. So again, particularly in view of the time zone that in fact most of you are in, very, very warm thanks for being with us and participating in this really difficult, complicated subject. Thank you very much.